We are back here in our Orion Uncover meeting in Leiden. My name is Álvaro Acar, and I'm the chair of this meeting. And we had an amazing day yesterday with a lot of interesting talks, and we are ready to start a new full day. Just to remind you that you can participate directly in this streaming. So if you look at the other side, I think here, you should be able to participate via the YouTube chat. And down, you should be able to also find our webpage where you can find all the information, program, etc. So we are ready to start. And I will bring in Steve Mears, who is our first speaker today. So Steve works at the JCMT and is Asia Observatory, and he will talk about highlights from the JCMT Transcend Survey. So Steve, if you can share your screen, I have it here. Yeah, so you put it in full screen, then you
can... Does that work?
Yeah, it all works, yeah.
All right, fantastic. Well, thank you very much for the opportunity to speak today. I'm sorry I couldn't be there in person, but my wife is nearly 9 months pregnant, so I thought it was better to stay on island right now. Today, I'd like to talk a little bit about the JCMT Transient Survey and some of the work that we're doing in Orion. So, what we're going to do is see the JCMT Transient Survey. I'll give it a little bit of an overview. Then I'll talk about a little bit of the automated pipeline that we have to search for variability. And then I'll talk a little bit about this fantastic flare detection that we had in the integral shaped filament before I'm going to bombard you with advertisements of papers that you should probably check out later. So, the JCMT Transient Survey is all about seeing the physical conditions of young stars in their earliest forming stages while they're still accreting mass. So I use this figure a lot from Lee Hartman's review in 2016 that shows accreting mass's path down to the young stellar object. So when stars accrete mass, most of it comes onto the disk first, and then through viscous interactions, it will travel down the disk to the magnetic field where it will be channeled onto the central source. You can imagine that none of this is a smooth process, and you have a viscous disk where things can, material can build up and then cause intermittent accretion bursts onto the central star, where you'll have some brightening and some fading, depending on how much mass is being accreted at any given time. So we'd like to understand this process a little bit more. One of the issues is that we don't have a lot of great telescopes in space right now to be able to survey and look at the far infrared portion of the spectrum where these stars reside. So what we're doing right now is using ground-based observations at a sub-millimeter telescope, the James Clerk Maxwell telescope. In this figure here, you'll see a star-forming core with a little protostar right at the center. And essentially, if a protostar goes into a burst phase where it starts accreting a lot of mass, the light from the central source is reprocessed by the cold surrounding dust. And then it'll warm that dust, and we'll be able to see that signal in the sub-millimeter at 450 and 850 microns. And we expect this based on some modeling that my former PhD supervisor, Doug Johnstone, did in 2013. We would expect to see this brightening taking place on scales of weeks to months. And before we started this survey, we knew that it was possible to see from Safran's paper in 2015 that compared APEX data with old SCUBA data as well, and already saw something brightening in the sub-millimeter. So the JCMT Transient Survey is looking at 8 different regions, all within 500 parsecs of the sun. In our total sample, we have about 1,000 young stellar objects, give or take. And then it's a 4-year survey so far, but we're currently going to be applying for at least a 3-year extension that starts in February of next year. And we visit each of these regions once a month, whenever these regions are observable in the sky. Now, 3 of these regions are in Orion. You can see the top of the integral shaped filament in the top left there. And then NGC 2024 and 2071, those are in Orion B. So I'll note that because we're visiting each of these fields for once a month for 4 years, this actually turns into getting the deepest sub-millimeter maps of these regions as well. So if you're not interested in time domain science and variability and things like this, we're also going to have very, very deep maps to do a whole bunch of ancillary science if you're interested. And a lot of this data is already public and becoming public as we progress. So how do we actually measure variability? Well, like I say, we take observations once a month. Here's our integral shape filament, the northern section of it. So first we need a catalog of sources to look for variability in light curves. So what we do is we co-add all of these different observations that we have into one image, and we find interesting looking structure, here highlighted in blue. That's essentially just a 5 sigma contour. Then I can use this source extraction algorithm called Fellwalker that was developed by one of our computer scientists at the East Asian Observatory at JCMT, which is a very robust algorithm for finding localized peaks. And what's really nice is that this works in this diffuse kind of gaseous region as well. So we've tested Fellwalker in a variety of different ways, and we've put in artificial sources and reconstructed maps, and it's a very robust algorithm to find these localized peak-like structures where we might expect something to brighten in this dust that you're seeing in this 850 micron region. Over all 8 regions, we have about 1,643 sources that we look for variability in. So we built this automated pipeline, and I want to stress that this happens automatically as soon as we collect data at the JCMT, because the telescope and the staff can do this kind of thing. Is we collect data, it automatically reduces, it automatically calibrates and aligns, and then performs 3 statistical tests for variability. We look for flux measurements of sources, each of those 1,600 sources that lay far away from their mean statistically. We've also built a standard deviation fiducial model of what we expect the standard deviation of a typical light curve to look like in these sources. And then we compare it against the measured standard deviation and look for outliers. And we also look for long-term trends. Now having nearly 4 years of data, we're able to look for real significant slopes and periodic signals and changing signal at submillimeter wavelengths. So if one of these tests flags a variable candidate source, an automatic email is sent out to the team as well that shows the source position, why it was flagged as a candidate, which test it passed or failed, depending on how you want to look at it. It also shows you where the source is located and where the nearest protostar and the nearest class 2 or 3 disk would be, based on the catalogs of McGath in 2012 and Stutz in 2013. So while tracking sources that appear in the COAD, it works. As these 2 light curves from Orion B will show you, these are sources HOPS 373 and HOPS 358, showing clear significant variation. The error bars on these points are between 2 and 4%. So this is actually a really good measurement at submillimeter wavelengths. We spent, well, a lot of time on that. A lot of my PhD thesis was trying to figure out how to calibrate submillimeter data better. But we don't just want to track the sources that appear in the COAD, because you might imagine that there's a source that's a 5 sigma detection in only 1 epoch. And once you co-add that with 9 other images, if you do the math, it turns out to be a non-detection in the COAD because it's blurred out essentially with the non-detections and all of the other images. So we run our source extraction algorithm in each individual image itself, and then we compare that catalog with the master, and we follow up on sources that do not appear in the COAD, but do show up at least once. And then you find things like this submillimeter flare event that happened in the integral shape filament. You can see the dates here is November 20th, November 26th, and then February the following year, where we have this significant brightening event that was coincident with a binary disk system known as JW566. Those square magenta squares there are class 2 objects from the Spitzer catalog. This system as well is also a previously known X-ray variable, but unfortunately we don't have any simultaneous optical, infrared, X-ray, or other radio data to look at. So if anybody is out there listening and knows of observations that took place on November 26th 2016, I would love to chat with you because I would love to see if we could get any more information on this flare object. So what's really nice about Scuba 2 and the JCMT is that we read out data every 30 seconds. So the JCMT continually scans across the sky and reads out data every 30 seconds. Well, with the help of Dr. Graham Bell, whom some of you may know, we selected the intervals that contain information on JW566 as the telescope scans across that area of the sky over this 30-minute observation. And we were able to construct a light curve over a minute-to-minute timescale. And we also, of course, did this for several typical field sources. I just include 2 here to show you that most sources in the field, or all of them except for JW566, have this nice flat light curve, whereas JW566 is a monotonic decrease. You can see that we didn't catch the flare at its peak. We caught it as it was already descending or fading. Because Scuba 2 takes data at 450 and 850 microns simultaneously, we can calculate a spectral index, which has a large error, but is effectively flat, which is consistent with non-thermal emission. And we can also approximate the brightness temperature by this ugly-looking equation. But all I'm showing here is that we can measure the flux and the time right off of this light curve here. And if we take the light crossing distance to be our solid angle, we calculate a brightness temperature of about 60,000 Kelvin. Of course, if this event happened on smaller scales than the light crossing time, which you might imagine if it's some sort of flare, I've also done this calculation for the radius of the star, which is 2.5 solar radii, and then the brightness temperature goes up significantly. If it was even on a section of the surface of the star, this flare, then this number would also increase. So what we decided is that the observations are definitely consistent with a magnetic reconnection event that we heard about a little bit yesterday in Jaime's talk, which was great. And the magnetic reconnection event here essentially just energizes particles and produces gyrosynchrotron radiation that we detect at a variety of wavelengths. We happen to be seeing it in submillimeter. So this is a paper earlier this year that was produced showing some of the modeling efforts on flares like this. And if you calculate the radioluminosity at 389 parsecs, which is about the distance of this source, you'll see that it has a very, very large radioluminosity. The most natural comparison point is the source GMRA that Jeff Bauer and team found in 2003, and it has a similar radioluminosity there. One fun one for outreach is that this flare we expect was 9 to 10 orders of magnitude more luminous than typical solar flares. So it would be off the right of this plot, but we're not sure what the X-ray luminosity would be because we have no coincident data with it as well. So a very exciting object, and we hope to be finding more. But I think that my time is running up. So what I'm going to do is just summarize with an advertisement for the JCMT Transient Survey. I'm not sure if we're going to be making available all of these talks or slides here, but I have clickable links here, or if you want to jot down any notes, you can come back to it on YouTube here. The survey overview paper, how we've done our data reduction and calibration to improve our, I guess, decrease our uncertainty by several factors. Some of the summary of the statistical tests that we run, variability over 4-year timescales using archival data, and then other interesting objects like we found, like a periodic variable in Serpens, an amazing detection of the stellar flare, which I was talking about a little bit. And we also have our claim to fame of the very first astronomer telegram that was ever released that has keywords YSO and submillimeter at the same time. So with that, thank you very much. I'll take any questions.
So thank you very much, Steve. Great talk. So perfect also in time. Just to answer your question, we want to collect the slides so we can put them on our webpage. So all the links should be available.
Fantastic.
So while we wait for some talks here in Leiden, we have a question from Marina Konkel, who is following us from Western Washington. So she asks, what is the time range for the variability for the Hopf sources?
Oh yeah, sorry. I guess I didn't show them in the plot here. But on these two hot sources, they start in, I guess we first observed this region in December of 2015, and that will go to August 2019. So across this scale here, I was kind of cheeky about not including the exact time frames because we haven't published some of this data, but this is over about a almost 4-year time scale, both of these sources here.
Really good. So are there more questions here in Leiden? So if not, I have one myself because I'm curious, because you look for peaks in your maps, and of course you try to link them to known protostars or known YSOs. But do you detect any recurrent peak that has no other counterpart? So can you detect things that are flaring and we need to learn more about them?
Really fantastic question. Yes, there's some work that I can't disclose too much information about right now, but there is some indirect evidence that we receive where we're seeing variability in a bright, compact, isolated object, or a couple of them actually, that have no known counterpart in the catalogs that exist so far. So it may actually be evidence of some either very, very young or very deeply embedded young stellar object that we may have information on in the submillimeter. Yeah, that's certainly possible.
Yeah, that sounds great, actually. So we are looking forward to hear the new results. And whenever you can disclose the source, we'll be happy to start observing.
Absolutely, it's part of a PhD student's thesis in South Korea, so I don't want to sell him out yet. Yeah.
So hopefully for the next Orion meeting, we can, or you can present, and you or your student can present the results.
I would very much look forward to that. Yeah.
Really good. So is there any more questions here from Leiden? Anybody who wants to talk about variability? We had excellent talks yesterday also about variability in different wavelengths, and I hope that this announcement that you make, or this request looking for more observation in different wavelengths at the same time, you find somebody and then you can complement the amazing result.
Yeah, thanks.
Good. Yeah, so thank you, Steve. Thank you very much. I will give you a big round of applause again here.
Thanks.
Good. So we go and move on to our next speaker. So Hidekai Takemura from NEOJ Sokendai, if I pronounce it correctly. You are muted, Hidekai. Yeah. Hidekai. Yeah. Okay, we are here. So if you share your screen, and I see it here. Perfect. Okay. So yeah, so as you can see, so Hidekai will talk about revisiting core mass function in Orion A using unbiased wide field CO observations. So you can start where you want.
Thank you. I'm Hideaki Takemura. I'm a second-year Sokendai master student working at NEOJ in Japan. Today I'll talk about the results of dense core survey toward Orion A, focusing on the analysis of core mass function. These are my collaborators of this study. This is the outline of my talk. First, I'll briefly tell you the importance of core mass function. And then I will describe the data and method of this study. Next, I will present the results of core survey focusing on the core mass function. Finally, I will summarize the main results of my talk. Okay, I will first tell you the importance of core mass function. Core mass function, or CMF in short, is a distribution function of core masses in a star-forming region. Previous studies revealed that the CMF has a turnover at few solar masses and declines with a power law index like IMF. The slope of the power law is similar to IMF. The facts suggest that the masses of the stars are determined at the stage of core formation. Therefore, it is important to understand what controls the formation of cores. Previous studies indicate that CMFs in nearby low-mass star-forming region have similar shapes and look universal. In this study, we want to know whether the core mass function had a turnover If they have, we want to know the masses. In this study, we used tree data of Orion A and assumed our emission are optically thin, Novema 45 meter data, Karman Novema combined data, and Alma and Iram combined data, which have a different resolution. First two data covered wide area of Orion A like light figure with C18O GA equal 120 line. And Alma data covers ISF integral shaped filament with N2H plus J equal 120 line. We applied dendrogram to these data with parameters shown here. And also we set additional thresholds to extract real structure. For N2H plus data, we used the isolate hyperfine emission to identify cores and estimate core masses. In this study, we defined a leaf as a dense core and separated identified cores into two groups, inside and outside the ISF. Next, I will explain how to calculate core masses. For C18 node data, we matched cores and made H2 column density maps derived from Hershey observation. For N2H plus data, H2 column density are calculated by following the same way as this paper here. In order to derive core mass function for gravitationally bound starless cores, we used Hopf catalog and performed simple visual analysis as shown here. And when we discuss low mass part and turnover of core mass function, we need to care about detection probability, of course, because confusion or overlap effect will be severe in a very small region. We inserted a 3D artificial Gaussian core to original image and applied the same core identification method to derive detection probability of cores. Then we checked whether the artificial core is detected. The size and total flux are changed for each mass bin. In one procedure, we inserted one artificial core and repeated 100 times for inside and outside the ISF. Finally, we just divided the number of cores by the detection probability to derive compensated core mass function. This is a result of core survey. The gravitationally bound starless cores are plotted as dots, and the images are integrated in density map of each line. In first two images, the cores inside and outside the ISF are plotted as a red and blue dot. The boundary is determined with a dendrogram hierarchy. The number of identified cores are shown in this table. We derived core mass functions for these colored cores. I'll show you the results. First, the left images are the results of this study with Novema data. The colors of plotted cores and core mass functions are same, and the green core mass function shows the core mass function for whole cores. As you can see, all core mass functions have Sabita-like power law indexes at high mass ends. In this region, we have previous works, which is shown in the right figures. The core mass functions of previous works and our core mass function for inside cores have a similar turnover, which is a few solar masses. So we can reproduce the similar core mass function as previous observation for similar regions with our methods. But the turnover masses between inside and outside are different. To check if this is real, I'll show the compensated core mass function. This is the result. The light blue and orange core mass function shows the compensated core mass function. As you can see, the shape and masses of turnover are changed. This means that turnovers are affected by confusion or overlap effect, and turnover may be generated by that kind of effect. And turnover mass can be smaller. So let's see the Comas function for karma data. As you can see, for Hymasen, Comas function has Sarpita-like slopes and turnovers at low mass part. Comas function for inside is flat around turnover, but the red and blue Comas function seem to have similar turnover masses, unlike Novayama case. Also, the turnover masses is different from Novayama's Comas function as shown in the right figure. Magenta Comas function shows the Comas function for Novayama data. This suggests that Comas function don't have a turnover at a few solar masses, but even with karma data, we cannot see clear turnover. So let's see the compensated Comas function. Also, unlike the Novayama data, the shapes below the turnover are similar to the original observed Comas function. From this results in this resolution, confusion effect is not so severe to change or the turnover. But the turnover masses seem to shift to low mass part a little bit. This means that the turnover masses can be smaller than these karma's turnover masses. So let's check the ARMA's data. Of course, we need to compare these two Comas functions carefully because the observed lines are different. But we can see the Comas function for ARMA data have a smaller turnover than karma's Comas function. Next, let's compare this Comas function with IMF for ONC, which is shown in the right figure. The IMF have a turnover at around 0.2 solar mass, and the turnover mass for the ARMA data, which is blue Comas function, is around 0.3 solar mass. So if we achieve 2 or 3 times higher angular resolution, we can check whether the Comas function has a turnover as a IMF in the same mass. This is a summary of my talk. We conducted dense core survey in Orion A to derive Comas function. We wanted to know whether Comas function has a turnover at low mass part. With our data, we cannot find the clear evidence of the existence of turnover of Comas function. But we can say that Comas function don't have a turnover at a few solar masses. And if we achieve 2 or 3 times higher resolution, we can not check whether Comas function have a turnover at the same mass as a IMF in Orion A. That's all for me. Thank you.
Thank you very much. It was a great talk. So we have, sorry, just a second. Yeah. So we have a question from Jan Forbrich, and I will read it to you. So he asks here from Leiden, so to what degree can you intercompare the core mass function in different subregions in Orion? And if so, is there any evidence for significant variations?
Sorry?
So Jan is asking whether if you take different subregions in the cloud and you calculate your core mass function, you see differences between, I guess, north, south, and different parts of it.
Yeah, like this. What degree? I mean, you mean the position of the cores?
I think he means from between the northern part and the southern part, or sub-regions within the southern part, because you have so many cores that you can run like subsets, right? So of your cloud, basically.
In this study, we do not separate the core into two groups according to the degrees. We only divided the core into two groups with the hierarchy of this crowd by using the dendrogram algorithm.
Okay. So are there more questions here from Leiden or from the audience? Please put them way in advance, because we have some delays between the broadcast and the YouTube video. If not, I have also one myself. So because you have these two overlapping maps now along the integral shape filament, and one from Karma plus Nobeyama and the other one with N2H plus.
Yes.
And you compare the statistics of the cores that you extract from them. My question is how much, how well your core extraction overlaps between the two tracers, because they are technically two molecules that might trace the same or might not. So if you can comment a bit on that.
Okay. In this figure, the southern part, I think the two cores matches well, but in the northern part, there are very few cores, C18 no cores, but there are a lot of N2H plus cores. So we need to check of the origin of the differences.
Mm-hmm. Yeah, no, that would be an interesting, I think, inter-comparison core by core to see, to understand the tracers also. So it's not only the cores, but to understand the tracers themselves, the observations.
Yes.
Good. So are there more questions around here? Okay. So if not, remember that we can. No, sorry. There is one question, I think, from Thomas Tanke. So he asks, so in the detection completeness test, did you account for the cluster distribution of cores rather than assuming a uniform distribution?
And we assumed Gaussian cores.
Okay. I think, but this is, he mentioned, I think, more on the completeness. Did you run the completeness test? And what are the assumptions, I think, in terms of completeness?
The completeness, we assume how to say, very uniform Gaussian core, but the property of the cores are changed for each mass bin according to the values derived from the identified cores.
So I think Thomas is following up. So he's asking again, so did you insert the cores at random locations or preferentially on the clusters and filaments? So just a uniform distribution, or you just favor some positions in your maps, basically?
So we inserted randomly for the inside and outside the integral shape of the filament. So for inside the integral shape of the filament, we randomly inserted the cores.
Okay, thank you. Yeah, we can continue either in the chat or, as you know, we're a Google group. So some more questions for Idekai. Please continue there. And so thank you very much, and that was a nice talk. Thank you.
Thank you.
Good. So yeah, we move on to our next speaker. So we have Sun Ishii. Hello. And you are.
Good morning.
Good morning. Hello. Nice to meet you.
Yeah.
So we have here your screen.
Yep.
So Sun Ishii is also from NAOJ, from Japan, and JAO. And he will talk about classification of cloud structures in Orion A and variation of the 13CO and C18O abundance ratio. So you can start whenever you want.
Okay. Yeah. Thank you for introducing me. I'm talking from Tokyo. So today I talk about the classification of cloud structure in Orion A and variation of 13CO over C18O abundance ratio based on the Nobeyama 45 45-meter telescope observation. Okay, so we carried out wide field observation using the Nobeyama 45-meter telescope. So using the CO multi-CO line, 12CO, 13CO, C18O, and N2H plus lines, we carried out wide field observation over the Orion A. So this map covers 2 to 3 degrees square, and the effective resolution is 22 arc-seconds, which is correspond to 0.04 parsecs. So based on this result, I carried out cloud identification within the Orion A molecular cloud. So we used certain CO data because this is a good tracer to internal structure through entire molecular cloud. So because 12CO, as you know, it's optically thick, so we used to derive excitation temperature. We used 12CO data to derive the excitation temperature. Yes, and also we have C18O, but this trace is more denser part. So in order to cover whole of the region of Orion A, we decided to use 13CO for this analysis. So we used the column density cube for 13CO to analyze the cloud structure. So we derived optical depths, and also we derived the column density like this. So then we applied SIMUS to identify the cloud structure. So yeah, SIMUS analyze the cloud structure based on the dendrogram result. So as a result, we identified 8 clouds in total, and left side, I show the result of the identification. And as you know, as you see, the well-known subregions are naturally identified as independent structures, such as OMC 1, 2, 3, 4, and 5, and also L1641 north, and also DLSF region. And the diffuse clouds outside of the internal shaped filament are also detected, and the small clouds appear to overlap with larger clouds. So this is a dendrogram of the result. So in total, we identified about 80 molecular clouds, and it tended to show the 3 groups in this dendrogram structures. So the first group is group 1, which is located the most right side of the dendrogram. This corresponds to clouds in the integral shaped filament, such as OMC 1, 2, 3, 4, and 5. And in the middle, there is some group of clouds. We call these groups as group 2. This corresponds to the clouds in the south and east-west side of integrated shape filament. And in the last, there is some group in the left side of the dendrogram. This includes, we call this group 3, and this group includes DLSF and other diffuse cloud outer part of the Orion cloud, Orion A. So in addition to this, some small structure isolated from other in the dendrogram, such as M43 shell and DLSF and the number 49 cloud. I highlighted these clouds. So because of why this structure was isolated from other groups, isolated means these clouds, for example, if we see the M43 shell, this is just located in the integral shaped filament, but in this dendrogram, this clouds belongs to group 2. So this is because of these clouds are isolated from the velocity structure. So this corresponds to this implies that these clouds are interacting with its region, and as a result, this has other velocity structure from others around, and in this, as a result, this belongs different groups. So our analysis is also useful to identify this kind of clouds which has a different velocity from others. So we applied we analyzed physical properties of clouds by groups. So this shows some physical parameter. The A left side shows the velocity dispersion versus cloud size, and the middle shows the size and the mass of clouds, and also right side shows the biliar parameter. The radius of identified clouds ranges from 0.07 to 1 parsec, with mean value of 0.3 parsec, and the cloud mass ranges from 0.3 solar masses to 860 solar masses, and the scaling relations show different feature between groups. For example, group 1, all clouds in group 1 shows a biliar parameter smaller than 2. This corresponds to these clouds are self-gravitating, and also group 3, this is shown in the blue, has a larger biliar parameter and tend to decrease with m to the -2/3. This seems to be corresponding to pressure-confirmed clamps. And for group 2, these clouds has features between group and group 3. So there is some difference between the groups. In addition to this, to investigate the environmental effect on the of the cloud, we analyze the data of abundance ratio, certain CO over CNTO. So the left panel shows the map of abundance ratio over the Orion A. So this ranges from 7 to 25. So as you see, the north part shows high abundance ratio, we already know this result from the Simaji et al. For example, Simaji et al. 2014, but we also can see the south distribution of abundance ratio in the southern part of Orion A. So this high abundance ratio would come from a selective dissociation of CNT on the H on PDR. So for UV emission, selectively dissociate CO isotopes, and the CNT molecules are expected to be selectively dissociated by UV photons. So this might be one reason for showing this kind of high abundance ratio. So if we see this abundance ratio for the individual clouds, so there is a large deviation by clouds, and within the cloud there is a high deviation even within the cloud, especially on the edges of the cloud show the high abundance ratio. And also this right panel shows the position velocity diagram of abundance ratio. So you can see the abundance ratio changes along the velocity. So now I'm showing the abundance ratio map for the individual clouds. So the cloud edge tend to show the high abundance ratio, and also there is some structure in the velocity direction too. Okay, so we compare with this abundance ratio with the dust extinction map and the FUV field derived by Haschel data. So this shows the abundance ratio and extinction by clouds. So the abundance ratio ranges from 5 to 25, and in the right panel show the correlation between the abundance ratio and extinction map. So there are two groups, which is one is a high ratio clouds. This abundance ratio decreases with dust extinction, And also, we can see that some groups that has a low abundance ratio. So these two correspond to the clouds in the high UV environment and clouds in the low FUV environment. So for the high the clouds that are irradiated by strong UV, it decreases with extinction. So there is another panel showing the same trend. So now x-axis shows the FUV strength, and vertical axis shows the abundance ratio. So if UV is strong, ratio goes to high. But if the cloud has a large dust extinction, it still shows a low abundance ratio. So this means this means a selective dissociation of CATO is enhanced on the surface of clouds that are irradiated by FUV, and it is suppressed under the low FUV environment. So this is a summary. So we identified 78 molecular clouds and using Simons, and the well-known internal clouds are naturally identified as an independent structure in Orion A, and isolated structures in the dendrogram are likely to be produced by the interaction with its region, and our large deviation of the abundance ratio is found among the identified clouds in the position velocity space, and the result support the selective dissociation of CATO on the surface of clouds, which is irradiated by FUV. Yeah, that's it. Thank you.
Thank you very much. Yeah, so we have several questions from the audience. So let me start. So one from Jan Orquist. So he asks, let me put you here in the screen. Yeah. He asks to, so is the dendrogram decomposition performed in the plane of the sky or in the PPV space?
Yeah, we carried out in the PPV space.
Okay, so it's a full decomposition, yes, considering velocities and all this stuff.
Yeah.
Really. Okay, so next question, because I mean the chat is fuming now with a lot of activity there. Second question is from Juan Diego Soler from Heidelberg. So is there any evidence of the interaction between the main filament clouds, so what you define as group 1, and the clouds surrounding it, so the group 2 of your decomposition?
Yes. Yeah. So yeah, there's no evidence that shows that all clouds interacted with others, but some clouds in the group 2 show some interaction from the group 1. So for example, M43 shell, which is located in the group 2, is having the expanding shell. So this might be interacting with the group 1.
But do you see any changes? Sorry, do you see any changes in the abundance ratios in these particular regions where they seem to interact, or,
yes,
or general changes?
Yes. For example, this shell shows a high abundance ratio outside part of the cloud, but this part is not so large, so angular resolution is not enough. So, but we plan to use a similar analysis using the Nobeyama plus Karma data, so which has a higher resolution. So we can determine such kind of structure using the data based on the Karma combined data set.
Really good. Yeah, we have another question, this time directly from Leiden. So Jan Forbrich asks, so have you compared spatial trends in the abundance ratio with the Herschel-based effective dust temperatures?
No, we didn't compare, but yeah, we can do this.
So I guess oops, sorry. I guess it's somehow also related with your G naught measurement, right? So there's some connection between your G naught estimates and the temperature. But that would be really interesting to see also these trends.
Yeah, that's true. Yeah, thank you very much.
Oh, really good. So if there are no more questions here from the audience, so we thank you again.
Thank you very much.
Good, and we move to our next speaker today. So we have Jan Orkis from Chalmers University. So I have you here. Let me put the stream. Yeah.
Do you hear me correctly?
Yeah, we can hear you well, and we see your presentation, so you can start whenever you want.
Okay, thank you very much. So hello everyone, I'm Jan Orkis. I'm a postdoc here at Chalmers University of Technology in Sweden. And I will be presenting you results about turbulence and star formation. And for a change, it's going to be about Orion B instead of Orion A. So this is part of the Orion B project, of which you can see all the members here. And this specific work has been mostly carried out by my student, Lee Olivier, and by myself. So a little introduction to this Orion B project. So that stands for Outstanding Observation, Outstanding Radio Imaging of Orion B. So that's 5 square degree mapping of the Orion B cloud. You can see our field here. The PIs of the projects are Jérôme Petit and Marie Bongerin. This composite image shows you the line emission from C18O, 13CO, and 12CO, but these are just 3 out of the several tens of molecules that we have mapped throughout this area. So I think this project holds the record for being the longest ever observed at the IRAM 30 meter with over 850 hours of observations. And that gives us a huge amount of data that we're trying to tackle in as many different ways as we can. You will hear more about that in the next session with Émeric Bron's talk. Just for those of you who aren't familiar with the geography of Orion B, that's the PDR created by Sigma Ori, which is OB star from the OB1C generation. That's, of course, the Horsehead. This and that are the NGC 2023 and 2024 star-forming regions. And here are the Orion B9 cores. The NGC 2068 star-forming region is out of our field to the upper left. Just a bit more technical details about our observations. So this field here is the smaller field that's been studied in the previous papers published by the Orion B collaboration. And the main things to take away is that their spatial resolution is roughly 30 arc seconds. So that's about 50 milliparsecs. And the spectral resolution is of the order of 0.5 kilometers per second. So now on to my main topic, which is turbulence versus star formation. Sorry. So, okay. Never mind. One thing that I need to remind you of is that any vector field, in particular a velocity field or a momentum density field, can be decomposed into its compressive part and into its solenoidal part. So that's the curl-free and the divergence-free parts. In the case of a fully developed turbulent velocity field, we are expecting at equipartition to have 2/3 of solenoidal motions and 1/3 of compressive motion. Quite intuitively, we can see that compressive motions are more likely to correlate with star formations, since gravitational infall and thermal expansion and outflows, all these things related to star formation, are compressive in nature, whereas solenoidal motions just steer the gas around without doing much. So this intuitive view is confirmed by simulations, which show that star formation starts earlier in compressive turbulence. The star formation rate increases, but interestingly, the IMF does not depend on the type of forcing, so there's no way of knowing from the distribution of stars in the cloud what was the nature of turbulence before stars formed in there. So that's all nice and good where we're dealing with simulations, but in the case of observations, how can we access this information when we don't have access to the entire 3D density field and velocity field? Well, thanks to a method developed by Brunton, Federat, and Price, we can try to infer 3D properties of the cloud based on 2D measurements. In particular, if we assume that the cloud is roughly isotropic and isolated, we can use the properties of the Fourier transform of the 2D field to measure properties of the 3D field. In our case, the quantity that we'll be measuring is the fraction of variance in the solenoidal mode of the momentum density field. For short, I will just be calling that the solenoidal fraction. So as a reminder, this is supposed to be 2/3 at equipartition. So 2 years ago, we did a pilot study using 13CO as a tracer, and it's been discussed in an Orion Hangout that you can access actually on the website currently. We found that for the entire field, the solenoidal fraction was quite high, which was consistent with the fact that Orion B has overall a very low star formation efficiency compared to other nearby clouds. But when we zoomed towards the star-forming regions, so NGC 2023 at the bottom and 2024 at the top, we saw that the solenoid fraction dropped dramatically, which means that the compressive motions become dominant. So it's all nice and good. We see a nice correlation between star formation and compressive motions. Then we wanted to expand on this study and make it on a larger field and with more molecular tracers. So we added C18O, which traces denser gas, and HCO+, which traces more the diffuse envelope of the cloud. And we performed the study in the entire 5 square degree field. So just for reference, these are the YSOs identified in Orion B, the youngest one being in red. So as you can see, a lot of star formation in NGC 2023 and 2024, a little bit in Orion B9, and not much happening to the left of the field. So we were hoping to see differences between the different tracers. For example, expecting the dense gas tracer to trace more compressive motions because it would be more subject to gravitational infall, for example. Now, how does it look? We started by repeating the measurement for our previous field. What we found with 13CO already, the result is different from the one we had 2 years ago. So that's the first problem that we still are working on to solve. And we see that HCO+ shows more solenoidal motions. C18O is also more solenoidal than 13CO. So that's something we didn't expect. When moving to a larger field, we see that the solenoidal fraction increases for all tracers. So there's less compression when we go towards the east. If we take our entire field, it's even less compressive. And if we focus on the eastern part, which is the least star forming overall, the solenoidal fraction that we obtain is extremely high for all tracers. So what can we conclude from that? First, it's nice to see that we see consistent behaviors for all tracers at all scales. So if we look at the entire regions of the cloud, all tracers behave in the same way. It also works when we zoom into specific regions. So here you can see a zoom on NGC 2024. For all tracers, the solenoidal fraction is dropping. It also works when zooming onto the Orion B9 cores. What I need to stress here is that at the stage things are currently, this is only a tool for comparative studies, and we shouldn't draw absolute conclusions from that, saying that, okay, the solenoidal fraction is exactly this as I would have measured it in a simulation. So we are not, this is not robust enough yet to be able to assess that. However, we can compare different regions, and we can compare, for example, NGC 2024 and Orion B9, which shows that the Orion B9 cores are clearly less compressive than NGC 2024. That could show that when you have only forcing, that is gravitational pull basically on the gas, things are not as compressive as when you have both, external driving and feedback from active star formation, as you can have in NGC 2024. So I mentioned the issue of the absolute measurements. Our main problem currently is dissipation scale of the gas, because basically we're measuring the solenoidal fraction in the motions down to our resolution, whereas we should be measuring it down to the dissipation scale, beyond which there's no turbulence anymore. So that's one of the main issues that we need to tackle currently. But the general conclusion, the qualitative conclusions hold. We can see that there's less and less compressive motions when we go to the east of the cloud, when we go away from the main star-forming regions, and that compressive motions correlate well in general with recent or future star formation. Now, if we put that in a bigger scope, could that indicate that Orion B is a young cloud? By young, I mean in a younger evolutionary stage than his big brother Orion A. So if we look at the filament population in Orion B, we see that these filaments are in general low mass, they are unbound, and they have no fertile fragmentation, which is what you expect from evolved filaments that are going to form stars in a more or less spontaneous way, spontaneous star formation from fragmentation into dense cores. We also see very little N2H+, which is the best tracer of cold and dense gas. So that also again shows that there are not so many accumulations of dense gas in the cloud ready to form stars, and the H2 regions are extremely young, and the fraction of particularly young class 0 YSOs in Orion B, especially in the NGC 2024 region, is particularly high when compared to, for example, Orion A. So all this tends to show that we have a cloud which is both chemically and dynamically young, in which spontaneous star formation in, for example, fragmenting filaments is not very active, at least not yet very active. And we see that the compressive forcing in present closest to the main PDR of the horsehead and to NGC 2024, which are the generations C and D of the OB1 association. So all that seems to show that star formation is rather triggered, and we go from one generation of stars to the other, so sigma already, then NGC 2024, and maybe the next generation is going to be more northeastwards from there. So that's all for me. Stay tuned for more Orion B results with Emmerich's talk later, and I will be taking your questions.
Thank you very much. So thank you also for being perfectly on time. And
oh, great.
To remind the audience that we have all these previous talks, and you were one of our speakers back then. We have all the links in our website as well, so it's part of the legacy of these Orion conferences, and in particular the legacy of this meeting. And again, the nasty thing is that we can compare what you said back then and what you are saying now. So if you are trying to have any other idea, then we can find it soon. No, but that's great. That's definitely great. So okay, so we have some questions here from Leiden. So I will try to read one to you. So one is from Jan Forbrich. So he asks, would it help to expand the characterization of turbulence to even more molecular tracers of different conditions?
Yes and no. I mean, we are already trying to do that, and one issue that we are facing is the intercalibration, so to speak, of the different tracers. As I mentioned, we are expecting C18O tracing the densest gas to trace the most compressive motions. It's apparently not the case, but the dissipation scale affects the different tracers in different ways. So that's something we're still working on. So once we manage to compare the behavior of already 3 tracers, we may be able to make a step forward and add more. But for that, we need tracers which are suitable for the study, which means that they should cover, they should have a good filling factor in the map, that they trace a large portion of the cloud. And they're not too saturated as 12CO, for example, because you cannot do anything about the dynamics of 12CO because of the opacity broadening of the line. So that doesn't leave many tracers, at least in our Orion B sample, doesn't leave many other tracers than these 3.
Really good. We have more questions now from the YouTube chat. So Juan Diego Soler, he asks, so would magnetic fields change the balance between compressive and solenoidal turbulence?
Yes, two things on that point. First thing is that when we are assuming that the cloud is isotropic, that means that we are assuming that the magnetic field is non-dominant. Otherwise, it's creating a strong anisotropy, or the assumptions don't work anymore. So since we are dealing here with a hypersonic turbulence, it should be fine because the sonic Mach number is the dominant factor. The other thing, yes, the magnetic field should be changing this balance at equipartition because so the gas will be more going around the lines than trying to compress them. Yeah, that would definitely change the balance. I'm probably not the best person to explain that, but we can discuss about that later.
Yeah, this could be also a topic that we can discuss here during these days. So since you are joining us,
yes,
we can go in much depth on this. So okay, we have even more questions. So again, from Leiden. So Joao Alves asks, so what is driving the turbulence, I guess, in the cloud?
So we didn't really get into this in details. It's a bit of a chicken and egg question when we look at the star-forming regions. As I mentioned, there's no real way to know what amount of compression comes from the external driving, basically that's gravity, or other kinds of shocks, and what comes from the internal feedback. When we're looking at the entire cloud, what we see is that since it's more compressive to the western edge, that's where the sigma array IC434 PDR is exerting pressure on the cloud. And then we see also increases in compression around NGC 2024. So there's at least one good candidate for driving the turbulence, at least for driving the compressive modes of turbulence, which is expanding H2 regions. But that's the only quite clear candidate that we have for that.
Yeah, actually, I had a following up question on this. I was thinking, because one of your first slides, you were showing the assumptions in the calculation, which is the isotropy in the cloud. And whether, yeah, this is was the next one, or one of the few next, yeah, this one.
Yeah.
So the isotropy and isolation, and the clouds are not isotropic nor isolated. And I was wondering whether you can also derive some kind of directionality of these, processes, and then link or try to identify the sources in that way.
No, that might be something that we could look into, but I have no idea how currently we could have diagnostics for the anisotropy and the directionality of the processes. But coming back to the isotropy and isolation assumption, well, the isolation that's quite easy to cheat with as long as you apodize the field properly, and that's actually a minor requirement onto the math that are behind this method. The isotropy is more of an issue because clearly the field is not that isotropic, but we checked it. Also, our power spectra, our 2D power spectra, are quite well isotropic in 2D, so we can safely assume that statistically they should be isotropic in 3D as well.
Really good. Yeah. So thank you, Jan. It was a great presentation. Thank you from Leiden again. Good. So we are moving on to our last speaker of this session. So we have Thomas. Hello, Thomas. Can you hear me?
Yes.
Yeah. Good. So if you can share your screen. So Thomas Tanke. So he's working at ESO, and he will talk about protostellar outflows in Orion A and B. If you can put it in full screen, as before. Now we see only half of your. There it is. Yes. Really good. Yeah. So if you can start anytime.
Okay, so I will be talking about even more CO data on Orion that has been collected in the course of the alcohol survey, which stands for Apex Large CO Heterodyne Orion Legacy Survey. I got credits for having the best and the worst acronym from the ESO and the Swedish tag, but I don't remember which one gave me which one. So it's thought to be a legacy survey with a large team behind it. There were many people on the proposal, and it also includes the SuperCam team and, of course, the Apex team. So the data were taken at Apex using the SuperCam instrument, which is a 64-pixel heterodyne receiver array working at 345 gigahertz. At the time of the observations, there were like 40 to 42 pixels really working. In total, I collected 12 million spectra, and the data were taken in December 2040, as I said, in ISO and in Swedish time. SuperCam is not a regular Apex instrument. It was just there for a visit. It is built at the University of Arizona. So for the survey itself, it is on the CO322 line at a velocity resolution of 0.25 kilometers a second. The beam size of Apex at that frequency is about 90 to 20 arc seconds. The coverage in total is 2.3 square degrees on Orion A, where I covered a large area south of 7.5 degrees of declination. So I do not have coverage of the Orion, the integral shaped filaments and L6041 North. So the coverage is on L6041 South. Because the stuff further north in Orion A has been covered by the JCMT already in that line, so we didn't want to duplicate. In Orion B, we have coverage on the main star-forming regions there, so NGC 2023, 2024, 2068, 2071. There's a smaller cloud further north, L1622, and also the Orion B9 area. So again, as for the coverage, so this shows the coverage in the Orion B cloud. We have seen this area just before the NGC 2024, 23, and the Orion B9. We also have coverage in the 2068 and NGC 2071 fields, and L1622 is somewhere up here. For Orion A, as I said, it covers the southern part down here, as the upper part basically has been covered by the JCMT at comparable resolution and sensitivity before already. The main goal of the survey is to get a complete count of molecular outflows in the giant molecular clouds. And I think one main thing that has not been attempted before is to really cover the entire extent of the molecular outflow. There are many surveys just either doing few outflows and covering them completely, or doing many outflows but covering only the central parts. So we wanted to have the entire outflow population of an entire giant molecular cloud in their full extent. And the other thing is, of course, that Orion has a very well characterized protostar population, mainly through the HOPS survey. And it also covers a variety of environments, like the relatively active star-forming regions in Orion B, the clustered regions, as compared to the very quiet, boring part in L6041 South. Do we detect outflows? Yes. So this figure shows the red and blue outflow, high-velocity CO emission in NGC 2068. And you can easily identify a couple of bipolar outflows, like up here, there's one, and there's a big one down there. There's maybe something going east-west here, and there's some less well-defined stuff, and that's where the stuff gets tricky, because if you want to do some statistics, you have to figure out what kind of high-velocity emission belongs to which protostar and to which outflow, which gets a bit tricky in regions like down here. We can do some detection statistics already. I have to say that a lot of this is still based on relatively preliminary data reduction, because I didn't get as far as I wanted to. But I think the general trends that I will be presenting will not change, while a few numbers may change a bit here and there. So for the detection statistics, or where do we find protostars, this plot shows kind of a so the triangles are Hobbs protostars that do have outflows detected, and the squares do show Hobbs protostars without outflow detection in the survey. And it's kind of relatively clear that there's a predominance for outflows to be detected in the protostars that have a low T-ball bolometric temperature, which is kind of an evolutionary indicator. So that's the youngest protostars. In numbers, in total, we have 170 Hobbs protostars covered, and see evidence for like 31 outflows that are relatively well defined. 20 of these outflows are from protostars with which kind of class 0, and only 11 are from protostars with class 1. In outflow in detection fractions, we find that 32% of the class 0 protostars have outflows, while only 11% of the class 1 or later outflows Hobbs protostars we see to have outflows. So again, there's a predominance for outflows to be found in the earlier evolutionary stages. Of course, I have to say that presumably more of the protostars do have outflows. It's just that the survey is not terribly sensitive. We can relate the protostar properties with the outflow properties, and one thing that we kind of recover is the well-known relation between the bolometric luminosity of a protostar and the outflow mechanical luminosity. So that's the energy input rate kind of, and as is well known, the mechanical luminosity goes up with the protostar luminosity. As for evolutionary trends in the outflow sample, I have to say that's not very clear. So there's various plots showing the momentum against the bolometric luminosity. So again, younger protostars are here, the older protostars are there. There's the momentum rate against the bolometric luminosity. There's the kinetic energy of the outflows against the bolometric luminosity. And there's the mechanical luminosity, so the energy input rate against the bolometric temperature. And I mean, there may be some trends for the less energetic outflows to be at later stages, but that's basically driven by a few points, like this outlier here and this outlier there. And if you take those away, then it's basically one bump. So I don't think I see very clear evidence for any outflow evolution yet. I have to say that, as I said, our goal was to measure the outflow properties over the full outflow extent, and it could be that some of the intrinsic trends are washed out by really going for the full outflows, because a lot of stuff might happen in the outflow lobe further out. It might disappear because there's no CO to be entrained anymore. It might be dissolved by UV radiation and all these things. So one thing that I still wanted to do is really to concentrate on the central parts around the protostars, as many other studies have done before. The final plot shows the kind of the ratio of the output energy input rate versus the bolometric luminosity of the protostars. And again, I don't see a real trend for any evolution of the kind of outflow efficiency, so the efficiency of turning the bolometric luminosity, so which reflects the accretion into outflow with the protostar evolution. The other thing that I wanted to briefly mention to show what else can we do with the survey is a study mainly led by John Belly, comparing CO data, including the alcohols data and carbon plus data taken by Sophia. And a number of other data sets like H-alpha data and JCMT's 13CO data. The same Sophia dataset, I should say, has been also analyzed by Pabst et al., who did PDR modeling, while John Ballymore looked at the morphology and the kinematics and trying to figure out what is where in this area. So if the field is basically here around the horse head, this is the CO data, where you can nicely see the horse head sticking out. You see the entire neck of the horse, and you see part of the body, so it sticks out very nicely. If you compare that with the Sophia data, you can just see the top of the horse's head as a very thin PDR, and then maybe like halfway down the head of the horse, the carbon-2 emission drops in. So the spatial morphology is very different. And other ways to show that are these plots. He created an amazing number of very colorful plots. So the plot that is interesting here is maybe this one, where you see in blue and in green, you see the CO emission. And in red, you see the carbon plus emission. And you see that, again, the horse head is sticking out here very nicely in CO. But in carbon plus emission, you basically see it up to the head embedded in the carbon plus emission. You can also see this in a different kind of plots. So this shows position velocity maps in various cuts across the horse head. So this cut goes along here. This shows the CO, where you see from the top of the mane all the way down into the cloud, you see a continuous stretch of CO, while in the carbon plus emission, you see the very tip of the horse's head, and then basically some very faint stuff, and then again further down, you see the main PDR. If you do the cut slightly offset from the horse head, so to the north of the horse head, you see CO only coming in relatively deep in the cloud, while the carbon plus emission extends much further out in the PDR. So that's what we saw also in the spatial maps.
Thomas, 30 seconds.
30 seconds. Okay. So, okay, I wanted to skip that anyway. So the basic picture that he drew up, so your viewpoint, if you can imagine, is in front of the screen and slightly from below. So what you see is some pillars sticking out of the cloud, and behind you see a bay of carbon-2 emissions. So that's where we see the CO only very deep in the cloud and a thick layer of carbon plus. So here at the ionization front, the carbon plus boils away rapidly. So you see it only a thin layer, while here in the bowl, the carbon plus emissions streams together, so you can see it over a much larger distance. So that's the basic picture that he draws from there. And this is my summary. So the ALCOLOS survey is a big survey in CO322. It's complementary to JCMT data. It is sensitive enough to detect protostellar outflows. It's a nightmare to reduce the data. And it can be used to go along with other surveys and data sets, and should have a kind of interesting legacy value, I hope. That's it.
So thank you very much. So we have a question from Steve Mears. So he's asking, and I'm also curious about this. So is all this alcohols data public, or is there a release plan that includes or excludes advanced data products?
In principle, not in principle, I mean, the raw data is available from the ESO archive, but I'm also planning, once I'm done with the data reduction finally, I'm also planning to release the reduced data cubes. So there's a way to release that through the ESO archive as well.
Yeah, so these are all exciting data. So I'm sure that many people want to have a look at them. And I have a question because I feel obliged to talk about filaments. And since you have outflows, now there have been several papers trying to identify whether the direction of the outflows are correlated or not, anti-correlated with the direction of the cloud structure. So do you see, now that you have enough statistics, you see any trend, or they are randomly oriented? Basically, whether we can trace the angular momentum from the cloud down to the protostars, or at some point this breaks down and they do not correlate?
Yes, I have not yet looked into that really for the alcohols data set, but I mean, like from my PhD thesis like 20 years ago, where I did similar stuff with infrared outflows, I didn't see any preferred orientation of the outflows over the Orion A cloud. So even in the integral shaped filament, I saw outflows going perpendicular to the filament and along the filament and at random angles to the filament. So my belief is that there's no preferred orientation, but I will have to look into this again.
Oh, okay, really good. Well, this is another topic that we can discuss here these days, because you are joining us in Leiden.
Yep.
So we thank Thomas again. And yeah, also, so thank you very much to all the speakers of this session. So we are now finishing, and we will resume in about 15 minutes. There's a new link on the website, so please follow us on YouTube. So thank you very much again.